Hello, everybody. It's great to be here. Thanks for having me. I'm Peter. I work with JavaScript, vanilla JavaScript mostly. I contract or I freelance from home, so I work from home in Holland. I organize JS1K, which is a code golfing competition. If you haven't heard of it, go and check the website. There are some awesome demos, and I'm sure you'll be busy till next week at least. Apart from that, I work a lot with parsing and with gaming, both playing and writing. So let's go on with parsing. I built a parser about 4 years ago called ZeParser. It's a JavaScript parser in JavaScript. I did it because I wanted to and because I wanted to build tools based on it, and there wasn't anything available that I could use myself as a basis for those tools. So I wrote it. It was and still is the fastest, or at least the current version is still the fastest. But the reason, or at least a reason for that, is that it has no parse tree. And I'd say that for most reasons that you want to use a parser, you actually don't need the parse tree. You're mostly interested in the tokens, at least for JavaScript. That seems to be the case. I chose for no parse tree, but while it's the fastest, it does mean that it's more of a problem to actually implement the parser. So it's harder to use because you have to be involved. You have to actually create your own parse tree or add your meta information as you need it. That's probably why you've heard of Esprima and not so much about ZeParser. I'm actually fine with that. As most parsers, the parser needs all the input to be available before you actually start parsing. So that means you actually have to fetch your entire file, which is fine for like your 1K file. But what about 40 megabytes of JavaScript? It takes a while for that to load in, and if your parser can't do anything before that, you're just wasting time. So for ZeParser, I've been doing stress testing to make sure that all the edge cases, and all the performance, and all the milliseconds I could gain are actually squeezed out of it. There are many different ways of doing parsing, and there are many different strategies, and the stress testing is really helping me. One of the things I've been doing lately is using a 40 megabyte file, which is an emscripten translation from C++ to JavaScript. And so you end up with this huge file, but the problem with that is it has a bias, right? It has a bias of the export that emscripten uses. So for example, that means that I might be optimizing my parser, but I'm now optimizing it against no white space or very little white space. So I wanted to do a beautification of that file in many different styles. White space, tabs, semicolon free, that sort of thing. And I just wanted to see whether or not my parser would hold up or just crumble whenever a certain style would be used. However, it turned out to be quite impossible to beautify that amount of JavaScript properly, because all the current parsers and all the current tools out there would just crash on memory as soon as you try to feed this file into them. Hence, I was going to start with a streaming parser and try to solve this. So this is what normal parsers do, or at least caching parsers do. They wait for all the input, and once they receive, they actually can start parsing, and then they can report that result to whoever is calling or using them. Enter streaming. Streaming is a low-level concept. I think it's already been touched 1 or 2 times during the conference. Everybody is using streaming basically, under the hood at least, because even if you read like 5 megabytes off your hard drive, you're not reading them in like instantly. You're still streaming like chunks, very small chunks of them, and then by the time that you have everything, your application is going to use them, show them, or whatever it does. So it's often abstracted away, and you don't have to mess with it if you don't want to. If you compare them, you can see that on the right-hand side it would be streaming, and you can actually use that time, that latency of receiving the chunks of your file. And by the time you're finished, you don't actually have to do anything anymore on the parsing end, which should at least save you a lot of time. So the problem here is that you need to be able to pause your parser, suspend it, at arbitrary points in the code. So you can't just say, I'm only going to pause it after, after every function, because that would be a nice chunk. You don't know that up ahead of time, and you can't really ask your network layer to say, oh, just give me in chunks of functions. It doesn't really work that way. So your parser needs to be able to yield, basically, but it needs to be able to yield across multiple multiple calls. An aspect of streaming is that it can have a low memory profile, because you don't actually have to cache anything, not just the source code, but neither the output, because as soon as you have a chunk and you parse it, you can push that out to the caller or whoever is using that parser. So your memory profile remains very low, and I've got a test where you can actually indefinitely keep parsing JavaScript and it won't run out of memory. And as I said before, another property is the latency. You're not wasting it as much as you otherwise would, because while you're waiting for the next chunk, you're already processing power. And this can be used in a variety of things. One would be like network optimizations. So if you have a real-time service that for some reason wants to parse and process JavaScript, it doesn't actually have to wait until that 1 megabyte GitHub file is in. It can actually start processing while it's being received, and that will only help for the end user. Other reasons are that pre-processing is already discussed, and the low memory environments like the Arduino, where memory is limited, and you can't afford to have the overhead that JavaScript simply has for large data structures. So parsing, the beast of parsing. Parsing basically consists of a tokenizer and a parser, right? You have a tokenizer that breaks your input, your source code apart in the smallest chunks, which we call tokens, and then we have a parser that takes those tokens and builds a parse tree. For the tokens, we have a set type of tokens, which are defined by the specification. The value of each token can have any value, as long as it's adhering to whatever type of token it is. So for a number, it can have any number of bytes, as long as there are only number bytes. Or in some cases of like hexadecimal, you can have like the X or that sort of thing. For the parser, it only works on tokens, so it doesn't actually have to worry about, for example, white space anymore. It just doesn't care. It only sees tokens. It will use those tokens and combine them into a parse tree. In JavaScript, they must work together. This is not always the case, not for every language, but for JavaScript, they must, simply because there is otherwise a conceived ambiguity in the /. So if you have a /, it may be a division, it may be a regular expression, and this is the reason why often the parser must work together with the tokenizer. So the parser must tell the tokenizer whether or not, if the next character is a /, it's going to be a division or a regular expression. Parsers excrete a parse tree, and this is arbitrary. There is no fixed rule or law on parse trees. It's basically just whatever you define it to be. If you want a parse tree which is a list of all the statement starts, then that is your parse tree. If you want a parse tree that is the exact specification, like all those names from the CFG, then that can be your parse tree. Probably not very useful, but it is whatever you define it to be. That's why for ZeParser, it's simply an array of tokens and nothing else. For streaming, parse trees can be a problem. The reason is actually quite simple. Let's say you have that 40 megabyte of JavaScript, and you want to wrap that in an anonymous function scope. Now you have a top-level token that never closes up until the end of the file, right? And so you can't really flush that node until the end of the file, or you're going to decide that you're going to decide that you're going to flush updates. You're going to say, okay, that token, I've added this and that node to it. Either way, it's not unsolvable. It's just, I don't think, really feasible in terms of streaming, because you're kind of defeating the point. You still have to cache, worst case anyways. So for ZeParser, I've made a transformation script which automatically translates the original parser to a streaming parser. It's not generic, so we're talking sort of DSL, a domain-specific language, but only in that there are certain rules for my code that I have to adhere to, because otherwise that transformation script will just fail. It will utterly fail. For example, my functions cannot return a Boolean because I use Boolean as a side channel to notify that it's actually a yield and not a natural return. This build script, it sanitizes some of my code. For example, it transforms the object-oriented nature of the code to a closure style. So you can have everything as a local variable rather than this. And it assumes that code style that I just mentioned. So it assumes that nothing is going to return a Boolean. The performance of that result is actually quite bad. It's unfortunate, but it's a necessity that I can't really fix easily. I'm not saying it's unfixable, but in order to emulate yield in ES5, you have to have a switch in a loop in a closure for every function call, and for every function call, again, you create a new closure. This is something that you're going to end up with regardless, because otherwise you wouldn't be able to do yield, and then you wouldn't be able to do streaming. There are some things we could do to improve this code. We could improve the post-processing. We could eliminate some dead code, or eliminate some cases where a function doesn't actually have to be a generator. But for most cases, post-processing does have an upper bound, and I don't think it's really satisfying. No, I don't think we're going to end up in a satisfying level. The alternative is hand coding and starting from scratch using the mechanisms that we still need to use, and trying to find an optimized path for achieving this streaming. But then that would have to be built from scratch, and I'm not going to do that myself. So generators, yeah, indeed. Generators have been touched on by Axel before, and I think one or two other people as well. So I'm not going to go deep into them, into generators, because I'm not actually going to use generators. I'm going to use something called coroutines, or at least that's the concept of it anyways. So JavaScript doesn't actually have threading, which means I can't just say suspend this code and then continue with that one, which would be kind of ideal for a streaming parser, right? You want to suspend you want to suspend the parser up until there's new information and new data, new input, and then continue the parser. We can't really do that out of the box. So we're going to use coroutines. And coroutines is basically where a generator can only yield through one call. A coroutine could yield through many calls at the same time. Of course, that's nearly impossible to do out of the box in JavaScript, even with yield. So in ES6, it would be slightly easier. For ES6, we'd only have to bubble the yield. For ES5, like I said, we have to wrap every code in a switch to do jumps, and then we have to wrap that into a loop to make loop still work, and then we have to wrap that in a closure to make sure that yielding works. So it gets a bit involved. So that's some code. This would be the normal function, just a synchronous ABC calls, whatever. In a generator, you could just yield between each of those calls, and in the end effect would still be a sort of synchronous, pseudo-synchronous execution. But then for coroutines, we want to yield inside that more function, which would also suspend the gen function. So you can see that it kind of means that all my functions in the parser are potentially generators now, and I have to approach them as such. It kind of means that I have to translate them that way, as well as for every function call that I make, even the most trivial function call, I have to approach them as generators. So I have to do, I have to call that function first to get another function back, and then that function I approach as if it was a generator. And in the translated code, you can later see that that actually becomes quite ugly. So let's just see what the translation ends up like. We have here a function that parses the carriage return. In the specification says that the carriage return may optionally be followed by a line feed, and if they do, it must be treated by a single token. It doesn't really matter why right now. That's what this function does. It's just 4 lines of code. You can, you could say it's actually 3 lines of code, whatever. This is what it ends up with being after the translation. A whole pile of cases. It works though. I mean, it works perfectly. It's a lot of code, and this is why it's just breaking optimization on every possible level, I suppose. So kind of what we want here is to do, no, sorry, for every part in the parser, every subparser, it kind of does this. It parses a part, it makes sure that it has enough input, and then it processes that input. But that suspended until enough input, it should be capable of doing a yield, and then it should be able to do a yield up until the original call site. In this case, would be parse, and it should be noted that you'll need a callback or a promise or whatever you want to use there, because the code right after parse may or may not run after the parser completes. You just don't know. You're going to be in asynchronous space regardless. So what would we need for a multi-level yield? Basically two things. We need to emulate the yield itself for ES5. So that for that, we're going to use switches, loops, and closures. And then we're going to need to bubble the yield to do the coroutine effect. The switch to jumps is actually quite easy. While JavaScript doesn't actually have jumps, so you can't really jump to an arbitrary line of code, or at least not out of the box. You could translate it like this. And as you can see, it would do exactly the same thing if you would run this. And as long as line is 1, it will start at the top, and since cases can be fallen through, the execution would still be the same thing. However, the reason we want to do this is because we want to wrap it in a closure. We want to make a closure over line so that if any of the functions inside would break for a yield, the next time we call this function, we can still continue at the same line. That's kind of the main trick, I suppose, for emulating yield. And this would be an example. We wanted, well, the test is doing A, calls A, then yields, and then calls B. And then you can see that if you call test the first time, you get this inner function back. And so if you call that one, it first calls A, then yields, so it returns. And then when you call it again, B. It's similar to generators. I'm guessing it shouldn't surprise you at this point. And on the right-hand side, you see what it would translate into, slightly abstracted, in my code. So you can see that it starts at line 1, and then in case 1, it will do the call to A. It will then return, or it will set line to 3. It will return false, or it will return, and then next time that you call F, the line will still be 3, so it will jump to case 3 and will continue with B, and then return naturally. This is basically how we yield in ES5. So the other thing that we're going to use is return type sniffing. Like I said before, there's an agreement in my style guide that no function inside of ZeParser can return a Boolean, and this is the reason. Whenever it returns false or true, it doesn't really matter, it means that the function is actually yielding and not returning naturally. So there's no return keyword that triggered it, there's no end of the function that returned it. If it returns false or true, it means that it yields. It means that the whole parser is going to be frozen, and that whenever you encounter this, that the yield must be bubbled to the top of the parse call. Essentially, this is what it does. Instead of doing, or instead of keeping it like inline log and then passing on the argument, the result value of calling foo, it needs to extract that call, put it into a new fresh variable, and then check if that result value is false. If it does, then propagate it by returning false rather than the original value, and otherwise call log with the value that was actually returned. So this is basically what we do all over the place, and how we propagate that yield from the tokenizer that wants the next character up until the root call of parse. For thawing, and thawing would be like the unsuspend or resume or whatever, we kind of do the opposite thing. So the inner function of each the inner function of each of those generators has an argument called yield value. And so when you call for the first time, as you see below, it calls it without an argument. It just starts it because there was no yield, so there's no need for a yield value. But the second time, it will have yielded at that second line where it says console.log yield. I'm going to replace that yield keyword with whatever value you pass on resuming. So below you see I pass on 5, and so that means that after the translation, that yield would end up with being 5, and it will log out 5, and then it will just return naturally. Well, it will return a string, and then that will be returned. So essentially, that is what is happening. So this is where you can find it. It's on GitHub, ZeParser 2. You can use the build to create the streamer. It worked last time I checked it, and it will output it to the build directory. For an endless parsing, you can use that file memleak, and you can see that it will endlessly parse, and intermittently it will print out the memory consumption stuff from Node.js. Yeah, I'm actually proud to have done this. It was a challenge because the whole streaming part, the whole coroutine part was a difficult thing to crack. If you ever dig into the actual translation script, you'll see that it's quite complex, and there are many edge cases that you have to take into account. But yeah, no, it works, and it seems to work properly. All the existing tests for the original parser that, of course, should also pass for this one, pass on any break. So like whenever there was a test, I also test for any break, arbitrary break in the original test. But in the end, it's still a toy project. So it's not really production ready, I would say, unless you're like super desperate. It's just something that I found fun to create, and so that's why I made it. I'm afraid that's about it. I'm not so bad on time, I suppose. Yeah, thanks for your time.
Hey, so you said that your parser is the fastest. Can you prove it?
Yes, actually, you could. If you go to, does that work? Yeah. Let's see. If you go to this one, it actually has a benchmark. I'm not going to pull in the 8 megabyte file here because that would be a waste of bandwidth. But as you can see, it lists a bunch of parsers. They are outdated. I'll completely admit that. I don't update this very often. And the problem here is that it's unfair to compare. So let me remove. Well, I can do this one. Let's just try it. Let's see what it does. So it will first fetch that file, which will take time over this network. And then we'll parse them a few times. So it's unfair to compare them simply because they do a lot more than ZeParser does, right? ZeParser cuts corners simply because it can. It doesn't create a parse tree. So here you see the numbers, and this is also a very old build of ZeParser, I'm sure. So it's I've always seen the Esprima benchmarks against my first version of ZeParser, which indeed is much slower. It's actually, isn't it in here? Oh right, there it is. So the first version is indeed much slower than this one. But I always hated it simply because it's not comparable. ZeParser was doing something for Xeon, which was a code inspection tool that I created, and Xeon just needed a lot of meta information, and so ZeParser did much of the legwork to get that information. And so I was troubled by that comparison. You can't really compare parsers unless they do exactly the same thing. And so that's why I figured I'm building ZeParser 2. It's going to do as little as possible, as fast as possible. So I'm pretty sure I can still claim that it's the fastest, but you're always going to have to take into account that other parsers do a lot more work. The actual problem here, or one of the biggest hurdles for performance, is creating those objects. So if it were ZeParser, you would actually create all the objects for every token. You would lose a lot of performance. It would still be faster. It would still be the fastest on this block, but you would see a drop in performance. And then if you would create a parse tree from those tokens, I'm sure that the performance would be, it would drop. So, but yeah, I'm still quite confident that it's the fastest on the block, if you would need so. But like I said, it gets involved in terms of implementing it and using it for your tool if you would need to.
So do you use it currently for any code transformations? How would you transform, for example, implement required JS conversion to ES6 modules or something like that.
I'm not sure how required.js uses a parser at all.
I mean, if this parser was plugged into another system that is intended to transpile JavaScript to something else, how do you plug in the parser? How do you work with this?
You mean how do you? What the API is for ZeParser?
Something like yeah.
Right. So I'd say it's fairly simple. You call the parse function, you pass on the input, and you get the tokens. And from these tokens, you'll have to do whatever it is that you want to do yourself. And like I said, for most cases, you're actually not interested in the actual parse tree. You just want those tokens. You want to. So for inspection, let me see if I can quickly. Probably not, because I wasn't anticipating live coding. But oh, come on, it's worked. See, yeah, there you go. So let's see. Correct. Is it legible? Yeah. So for example, if bar, if we wanted to do a linting, right? It's one of the easiest things that you might want to use a parser for. You don't want the entire parse tree because you'd have to traverse the entire parse tree. Instead, what you want to do is I'm at the closing parenthesis, and I want to see if this coder actually used a curly bracket or put or did something like this, something like very, very bad. Never do this. If you want to detect this, you don't want to traverse the entire parse tree. You want to see, does the next token start on a new line, or is the next token a curly bracket? And so for many of those linting cases, this is what you want to do. Actually, there's a talk. I'm pretty sure it's Xeon.js talk for JSConf. If you're interested, go and watch that. I go in depth on this matter.